Mars is not what you think, but not for the reasons often implied. What most people learn about Mars is based on simplified summaries drawn from early observations. Those descriptions were shaped by the limits of telescopes, indirect measurements, and incomplete data. As spacecraft began observing Mars directly, using calibrated instruments and repeatable experiments, many long-standing assumptions were revised. The planet itself did not change. The methods used to measure it did. Understanding Mars today requires understanding how those measurements were made and how improved data reshaped earlier conclusions. Today, Mars serves a different purpose. It is a reference case for how planetary science develops when observations improve, instruments become more specialized, and measurements are compared across multiple methods. Modern knowledge of Mars does not come from a single experiment or mission. It is the result of layered data collected over decades, using tools designed to measure specific physical properties. Mars illustrates how conclusions change as measurement techniques become more precise. Before spacecraft exploration, Mars was studied using ground-based telescopes. Astronomers recorded its seasonal changes in brightness, variations in surface markings, and shifts in apparent color. These observations provided limited information. Earth's atmosphere reduced image clarity, and resolution was constrained by optical technology. The planet's reddish appearance led to the assumption that the surface itself was uniformly red. Atmospheric properties were inferred indirectly, using contrast changes and albedo measurements rather than direct sampling. These methods allowed only general conclusions. They could not determine surface composition, atmospheric density, or chemical processes with accuracy. By the mid-20th century, Mars was broadly described as a cold planet with a thin atmosphere and limited surface activity. This view was based on thermal measurements, spectral data, and comparisons with Earth and the Moon. However, without direct measurements, many aspects of these conclusions remained provisional. The primary limitation was not incorrect reasoning, but insufficient data resolution. The transition from indirect observation to direct measurement began with spacecraft missions. Early flybys provided the first close-range images, revealing surface features at resolutions impossible from Earth. Orbiters followed, enabling repeated observations under controlled lighting and seasonal conditions. Landers and rovers then delivered instruments directly to the surface, allowing in situ measurements. Each stage reduced uncertainty. Flybys established basic surface morphology. Orbiters mapped large regions consistently. Surface missions provided ground truth, confirming or refining orbital interpretations. When the first landers returned color images, differences appeared between early image releases and later calibrated versions. This discrepancy was not due to faulty instruments. It reflected the complexity of converting sensor data into human visible color. Camera sensors respond to specific wavelength bands that must be translated using calibration targets and models of illumination and atmosphere. Early images were processed quickly for public release. Subsequent recalibration used onboard reference targets with known reflectance properties. This allowed scientists to correct for lighting conditions, dust in the atmosphere, and sensor response. From this process emerged a central principle of planetary science. Images are quantitative measurements. Color, brightness, and contrast are data products that require calibration and interpretation. With improved calibration, attention turned to the Martian atmosphere. Mars has an atmosphere composed primarily of carbon dioxide, with a surface pressure less than 1% of Earth's. Gas molecules alone cannot account for the observed sky color. Instead, the dominant factor is suspended dust. These particles are typically a few micrometers in diameter. Their size places them in a scattering regime different from Earth's atmospheric molecules. On Earth, Rayleigh scattering by small molecules favors shorter wavelengths, producing a blue sky. On Mars, larger dust particles preferentially absorb shorter wavelengths and scatter longer ones. As a result, the daytime sky appears yellow-brown. This effect has been measured directly using calibrated cameras on the surface and verified using radiative transfer models that incorporate particle size distributions, dust density, and composition. At sunset, illumination geometry changes. Sunlight passes through a longer atmospheric path, and forward scattering becomes dominant near the sun's position. Under these conditions, shorter wavelengths are scattered toward the observer, producing a localized blue tint around the sun. The remainder of the sky retains its usual color. This phenomenon has been observed repeatedly and modeled quantitatively. It allows scientists to estimate atmospheric opacity, dust concentration, and seasonal variability. These values are derived from repeated measurements under known conditions and validated against physical models. No single observation is sufficient on its own. The same measurement-based approach applies to water. Orbital images first revealed valley networks, outflow channels, and delta-shaped deposits. On Earth, such geometries are associated with erosion and sediment transport by liquid water. However, morphology alone is not conclusive. To strengthen interpretation, researchers compared elevation profiles, branching angles, sediment thickness, and spatial distribution. These analyses showed consistency with fluid flow under gravity. Surface missions provided additional confirmation. In polar regions, robotic arms excavated shallow trenches, exposing bright material that sublimated when exposed to sunlight. The rate of loss matched expectations for water ice. Elsewhere, rovers drilled into rock and soil. Heating samples released water vapor, allowing direct measurement of water content by weight. Orbital spectroscopy added further constraints. Instruments detected absorption features consistent with hydrated minerals. Radar systems measured subsurface reflections interpreted as ice-rich layers. Each technique had limitations. Spectrometers probe only the upper surface. Radar has limited spatial resolution. Surface instruments provide precise data, but only at specific locations. Together, these observations form a measurement chain. Confidence increases when independent methods converge on consistent results. Explaining the present instability of liquid water requires understanding atmospheric loss. Dedicated missions focused on plasma physics have measured how the solar wind interacts with Mars's upper atmosphere. Orbiters equipped with particle detectors observed multiple escape mechanisms. Neutral atoms can gain sufficient energy to escape gravitational binding. Ionized particles can be carried away by electromagnetic interactions with the solar wind. The rate of loss varies with solar activity and atmospheric conditions. The MAVEN mission provided continuous measurements of these processes. It quantified present-day atmospheric loss rates in grams per second and documented increases during solar storms. These measurements are direct and repeatable. To understand long-term effects, these rates are scaled using models of early solar output, which was higher than today. When integrated over geological timescales, the cumulative loss is substantial. This conclusion is supported by isotopic measurements. Lighter isotopes escape more readily, leaving behind an altered isotopic ratio. These ratios are measured directly and provide independent confirmation of long-term atmospheric loss. Earlier models described Mars in broad terms. Measurement-based analysis replaced these generalizations with quantified systems. Surface color is now understood as a thin optical layer rather than a bulk property. Atmospheric behavior is treated as a dynamic interaction with solar radiation. Water is recognized as present in multiple physical and chemical states, each detectable by specific instruments. Uncertainty remains, but it is constrained. Scientists can identify which questions are resolved and which require new data or improved methods. This distinction guides mission design. Habitability is addressed using the same measurement framework. Radiation exposure is measured directly using surface dosimeters. These data show higher radiation levels than on Earth due to limited atmospheric shielding and the absence of a global magnetic field. Soil chemistry is analyzed using onboard laboratories. Perchlorates are identified through wet chemistry experiments and confirmed spectroscopically. Dust properties are characterized by observing accumulation rates, particle size effects, and electrostatic behavior on instruments and solar panels. Each parameter is quantified, none are treated qualitatively. The challenge is to measure constraints accurately enough to inform engineering solutions, such as shielding, filtration, and resource extraction. Sample return addresses, remaining limitations. Instruments on Mars are constrained by mass, power, and sensitivity. Returning samples to Earth allows isotopic analysis, trace organic detection, and mineralogical context to be examined together, reducing ambiguity. Mars provides a clear example of how planetary science advances. Early observations established basic characteristics. Subsequent missions improved resolution, accuracy, and scope. Each dataset was integrated with existing knowledge rather than replacing it.